The universe feels eternal. The stars above seem fixed, their light pouring endlessly across the night. Galaxies swirl in silent spirals, nebulae bloom with radiant color, and space stretches on without boundary. To the human eye, there is no hint of fragility. Yet science tells us a different story. The cosmos is not immortal. Its brilliance is borrowed, its energy finite, its fate already unfolding in ways we can scarcely perceive. Every star that shines is consuming its fuel. Every galaxy that drifts is carried by an expansion whose future we cannot predict. And beneath the order we see lies a deeper law: entropy, the gradual unweaving of all structure, the quiet guarantee that nothing lasts forever. There are many endings written into the language of physics. Some whisper of a slow fade, where stars extinguish and the universe sinks into cold darkness, a heat death of endless silence. Others warn of collapse, a big crunch where galaxies fall back upon themselves in a final firestorm. Still others speak of more violent fates, a big rip tearing atoms apart, or a sudden vacuum decay, rewriting the laws of reality in an instant. The universe will end. The only question is how. This is the story of endings beyond imagination, of fire, of silence, of collapse and dissolution, a meditation on the last chapters of existence itself, the illusion of permanence. The night sky tells a lie. When we look upward, we see stillness. The constellations appear eternal, the same patterns traced by our ancestors thousands of years ago. The Milky Way stretches in a luminous river across the dark, its countless stars woven into a tapestry that seems unchanging, immortal. But this vision is an illusion born of human limitation. The universe is not static. It is restless, dynamic, and impermanent. Its permanence exists only on timescales so vast that human lifetimes, even entire civilizations, are too brief to perceive the change. Every star we see is in motion, hurtling through space at thousands of kilometers per second. Over millions of years, constellations warp and dissolve, their familiar shapes unraveling. Galaxies themselves are not fixed. They collide, merge, and reshape one another in dances that span billions of years. To us, the sky feels frozen. In truth, it is alive, flowing like a river whose currents move too slowly for us to notice. At the heart of this impermanence is entropy, the tendency of systems toward disorder, the second law of thermodynamics. Entropy is not destruction, but a direction, the arrow of time. Stars burn because they convert ordered hydrogen into helium and radiation, spreading energy outward. Black holes form because gravity collapses matter into denser states. Galaxies evolve because energy disperses, clouds collapse, and matter rearranges. Entropy ensures that the universe is not eternal in its present form. Even the starlight itself is a reminder of change. The photons striking our eyes tonight began their journey thousands, sometimes millions of years ago. Some of those stars may already be dead, their light a ghost still crossing the gulf of space. The sky is less a window to the present than a record of the past, showing us what once was, not what is. Cosmic permanence is an illusion because of scale. To a mayfly, which lives a single day, a mountain appears eternal. To humanity, living for millennia, stars seem immutable. But to the universe, which measures time in billions of years, even stars are fleeting. Their fates are already sealed from the moment of their birth. Hydrogen burns, fuel is consumed, and the delicate balance that sustains them will one day collapse. And it is not only stars. Planets too are impermanent. Worlds are shaped and reshaped by impacts, by tectonic forces, by their suns. Earth itself is temporary. Its oceans will boil away under the swollen sun. Its surface will melt. Its crust will eventually be recycled into nothing recognizable. In time, even the atoms that compose it may decay. What then of galaxies? They too will not endure. The Milky Way and the Andromeda Galaxy are already on a collision course, destined to merge in about 4 billion years. Their stars will not crash like cars on a highway, but their gravitational tides will warp and stretch them into new forms. Beyond that, all galaxies drift apart as the universe expands, carried away on the currents of spacetime. On the grandest scale, structure itself is impermanent. The illusion of permanence comforts us. It allows civilizations to chart the heavens, to plant crops by the stars, to dream of eternity. But science pulls back the veil. The universe is impermanent, written in the mathematics of entropy, in the ticking clocks of stars, in the relentless expansion of space. Everything changes. Nothing lasts forever. What we call permanence is merely the slowness of change compared to our brief lives. But to the cosmos, permanence is an impossibility. For most of human history, the heavens seemed eternal. Ancient peoples lifted their eyes to the night sky and found order, constancy, and permanence. The stars returned each season, guiding harvests, navigation, and ritual. Constellations carried myths across generations, unchanging symbols of divine will or cosmic law. To early civilizations, the heavens were not only eternal, they were perfect, untouched by the corruption and decay that marked life on Earth. The ancient Greeks spoke of the sphere of the fixed stars, a crystalline dome where celestial lights shone with eternal clarity. In China, dynasties tracked guest stars and comets, yet still believed the greater fabric of the heavens endured unchanged. Even in medieval Europe, the sky was thought to be immutable, its lights fixed since creation. To the human eye, spanning mere decades, stars did not seem to move, dim, or die. The illusion of permanence was complete. It was only with careful observation and the birth of science that cracks in this illusion appeared. Tycho Brahe, in 1572, recorded a new star that blazed in the constellation Cassiopeia. It was a supernova, though the term had not yet been coined. To him, it was proof that the heavens were not unchanging. Centuries later, telescopes revealed variable stars, pulsing with rhythms of expansion and contraction, their brightness shifting over years. The perfect eternal sky gave way to a dynamic, restless cosmos. The illusion of permanence persists today, though in subtler form. We look up and still see familiar constellations. Orion strides across the winter sky as he did for the Babylonians. The Big Dipper wheels above the northern hemisphere, as it has since humanity first told stories under its stars. But modern astronomy tells us these shapes are temporary. Stars within them move at different speeds, bound by different orbits. In a few 100,000 years, the constellations we know will be unrecognizable. The night sky itself is a work in progress, shifting invisibly to human timescales. On grander scales, the impermanence grows starker. Galaxies are not static islands. They collide, merge, and tear each other apart in tidal dances of unimaginable violence. Our own Milky Way is already locked in such a fate, destined to collide with Andromeda. Over billions of years, the two spirals will merge into a new, elliptical galaxy, reshaping the night sky into something no human eye will ever see. To call the heavens permanent is to overlook the dynamism of cosmic history. Even deeper lies entropy, the slow but inexorable decay written into the fabric of physics itself. Stars consume their fuel. Matter decays into simpler states. Energy spreads. The illusion of permanence is a trick of perspective. We live in a fleeting moment where galaxies are bright, stars are abundant, and life is possible. But this is a chapter, not the book. The universe will not always look as it does now. Philosophically, the illusion comforts us. We seek constancy in a world of change. The stars seem eternal because we long for eternity. They anchor myths, religions, and cultures precisely because they do not change on human scales. Yet science asks us to confront a deeper truth. Permanence is impossible. Change is the only constant, even for the cosmos itself. When we lift our eyes to the night sky, we are not witnessing an eternal dome, but a fleeting arrangement of fire and gas, fragile in the face of time. Every star is already dying. Every galaxy is already moving. Every atom is already shifting toward entropy. The illusion of permanence is the first veil we must lift to understand the end of the universe. Only then can we grasp the truth. The cosmos is mortal, and its endings are already written into its laws. Heat death, the silent fade. The most widely accepted vision of the universe's ending is not fire, but silence. Not a violent collapse, not a catastrophic tearing apart, but a slow, inexorable fading. Physicists call it the heat death, or more formally, the Big Freeze. It is the universe's quiet surrender to the second law of thermodynamics, the law of entropy. Entropy is not destruction, but dispersal. It is the measure of disorder, of energy spread so evenly that no useful work can be done. In the early universe, after the Big Bang, entropy was low. Matter clumped into stars. Stars clustered into galaxies. Galaxies wove themselves into filaments and voids. Structure flourished. But as time stretches forward, entropy grows. Energy dissipates. Order erodes. And eventually, if the universe continues expanding forever, all differences, temperature, energy, light, will smooth into uniformity. The timeline of this ending unfolds across unimaginable scales. First, the stars die. Red dwarfs, the longest lived, will endure for trillions of years, glowing faintly while larger stars vanish. In the distant future, the universe will be lit only by these tiny embers. Then they too will fade, leaving behind white dwarfs cooling into black dwarfs, dark, invisible relics scattered across the void. Galaxies will dim as their fuel is exhausted. No new stars will ignite, for the raw hydrogen clouds will have been spent. Supernovae will cease. Stellar nurseries will fall silent. What remains will be a universe of stellar corpses, white dwarfs, neutron stars, and black holes. Even these remnants will not last forever. Black holes will dominate for eons, slowly evaporating through Hawking radiation. Over timescales measured in 10 to the 100 years, they too will vanish, leaving nothing but the faintest glow of low-energy photons. The heat death is not a violent end. It is a long dusk, a gradual dimming of the cosmos until no light remains. It is eternity as silence, not explosion. A universe that ends not with a bang, but with a whisper. The heat death is the most haunting of all cosmic endings, precisely because of its quiet inevitability. Unlike the violence of a big crunch or the chaos of a big rip, heat death does not arrive in a single moment. It creeps forward invisibly, hidden in the arithmetic of thermodynamics, unfolding over spans of time so long they defy comprehension. At the heart of this vision lies the second law of thermodynamics. Entropy must always increase. This law does not care for stars, galaxies, or life. It is universal, absolute. Stars shine because they burn fuel. creating gradients between hot and cold. Galaxies form because matter clumps in regions of higher density. Life itself exists because of the flow of energy from one state to another. But eventually, those gradients smooth out. The cosmos approaches equilibrium, and in equilibrium, nothing new can happen. Dark energy accelerates this march toward silence. Since the late 1990s, astronomers have known that the universe's expansion is speeding up, driven by a mysterious force that permeates space-time. As galaxies race farther apart, fewer and fewer will remain visible to one another. Trillions of years from now, distant galaxies will vanish beyond cosmic horizons, their light forever unreachable. The universe will become a lonely place, each galactic island isolated, cut off from the others by expanding space. In this future, stellar formation ceases. No new suns will ignite. The remaining stars burn out, one by one, until only stellar remnants remain. White dwarfs, neutron stars, and black holes. Even they, given enough time, will fade or evaporate. The black hole era will end with their disappearance into radiation. Matter itself may not survive. If protons decay, as some theories predict, every atom in the universe will dissolve into a sea of particles. What remains is not fire, but shadow. A universe so vast, yet so empty, that temperature differences vanish, energy disperses evenly, and no structure remains. A cosmos reduced to thin radiation stretched across expanding space, endlessly cooling toward absolute zero. Philosophically, this end is chilling. It is not violent, but indifferent. The heat death asks us to imagine eternity as nothing but silence and darkness. A universe stripped of novelty, where even time itself loses meaning because nothing happens. Yet there is beauty in this vision too, a reminder that everything we know, stars, galaxies, life, exists in a fleeting golden age, a brief window of brilliance between the fiery beginning of the Big Bang and the cold silence of the far future. To live in such a universe is both humbling and extraordinary. We are born in the middle chapters of a story whose ending is already written, yet whose details remain mysterious. Heat death is not simply doom. It is the final breath of a cosmos that once burned with light. The Big Crunch, a violent return. The universe as we see it today is expanding. Galaxies recede from one another. Space itself stretches, and the cosmic fabric grows ever larger. Yet for much of the 20th century, scientists wondered, might this expansion one day halt and even reverse? Could gravity, the force that binds galaxies, stars, and planets, eventually overcome the outward push and pull everything back together? This possibility is known as the Big Crunch, a violent return in which the universe collapses into itself. The idea begins with gravity's persistence. Every star, every galaxy, every particle pulls on every other. Though expansion currently dominates, gravity never ceases. If the universe contained enough matter, if galaxies and dark matter were dense enough, this pull could slow expansion over billions of years. The galaxies would decelerate, their outward flight halted. Then, in a reversal of the Big Bang, they would begin to fall inward. What would follow is cosmic catastrophe. Galaxies would rush toward one another, colliding in tidal chaos. Stars would be flung from their orbits or torn apart. Black holes, already the most dominant objects in galaxies, would merge, swelling in mass as they consumed everything near. The night sky, far from dark, would blaze with the light of a universe crashing together. As collapse deepened, the cosmic microwave background, the faint afterglow of the Big Bang, would no longer stretch thinner, but grow hotter. the temperature of the universe would rise, reversing billions of years of cooling. Galaxies would condense, stars would collide, and eventually the cosmos itself would shrink into a fiery, dense state. Some models predict that the final seconds would mirror the first, a singularity where space and time themselves fold into one. To imagine the Big Crunch is to imagine symmetry. The universe begins with an explosion, expands for eons, and ends in implosion. It is a cycle of fire, beginning and ending in singularity, perhaps destined to repeat in an eternal series of bangs and crunches. For some, this vision is comforting, an endless rebirth of universes. For others, it is terrifying, a final collapse into unknowable density. The Big Crunch remains speculative, its likelihood dependent on cosmic balance. The discovery of dark energy, the mysterious force accelerating expansion, has made it seem unlikely. Yet the concept lingers, a reminder that gravity is patient, and that the universe's fate is still written in equations we do not fully understand. If expansion halts, the universe will not end in silence. It will end in fire. The Big Crunch is not merely a collapse of matter. It is a collapse of time, of space, of the very structure that allows events to unfold. To understand why such an ending was once considered plausible, we must step deeper into the mathematics of cosmology, into the balance between expansion and gravity. In the early 20th century, Einstein's general relativity offered a framework to describe the universe as a whole. It revealed that space-time itself is dynamic, bending and curving under the influence of matter and energy. When Edwin Hubble discovered that galaxies are receding, it became clear that the universe was expanding. The question then emerged: would this expansion continue forever, or would gravity one day reverse it? The answer lies in density. Cosmologists speak of a critical density, a delicate threshold between eternal expansion and ultimate collapse. If the average density of matter and energy in the universe were greater than this value, gravity would eventually slow expansion and drag everything inward. If lower, expansion would continue forever. For decades, measuring this density became one of the central quests of astrophysics. Dark matter complicated the story. Observations of galaxies revealed they contained far more mass than visible stars and gas could explain. Invisible dark matter, outweighing normal matter by a factor of 5, strengthened gravity's pull. For a time, it seemed possible that the universe might indeed contain enough matter to halt expansion, to bring about a cosmic reversal. The Big Crunch appeared to be a genuine possibility. But then came the discovery of dark energy in the late 1990s. Type Ia supernovae, stellar explosions used as cosmic yardsticks, revealed that expansion is not slowing, but accelerating. A mysterious pressure, woven into the fabric of space-time itself, is driving galaxies apart faster and faster. With dark energy in play, the Big Crunch receded into improbability. Expansion will not halt, it will accelerate. Still, theories of the crunch linger. Some models suggest dark energy might not be constant. If it were to weaken over unimaginable spans of time, gravity might regain dominance. If dark energy reverses its nature, changing sign from repulsion to attraction, it could even hasten collapse. These speculations remain beyond present evidence, but they preserve the idea that the universe's fate is not fixed. The philosophy of the Big Crunch carries its own strange beauty. It envisions the cosmos as cyclical, not linear, born in fire, dying in fire, reborn again. In such models, the end is not absolute, but transitional. The final collapse may seed another Big Bang, another expansion, another universe. Eternity becomes a rhythm of bangs and crunches, an endless heartbeat of creation and destruction. Whether this vision is true remains uncertain, yet the thought itself reshapes our perspective. The Big Crunch, if it occurs, is not merely an end, but a mirror, time folding back on itself, history collapsing into origin. It is an echo of beginnings. The Big Rip, when space itself shatters. Among the possible ends of the universe, few are as terrifying as the Big Rip. It is not a collapse, nor a slow fading into silence, but a catastrophic unraveling of reality itself. In this vision, the same mysterious force that drives the expansion of the universe, dark energy, does not remain steady. Instead, it grows stronger, accelerating the cosmos until even the bonds that hold matter together are torn apart. The idea arises from the late 20th century discovery that expansion is accelerating. Galaxies are not just moving apart, they are doing so faster and faster. This acceleration implies that some unknown energy pervades spacetime, exerting a repulsive effect. Cosmologists call it dark energy, and though its nature remains mysterious, it makes up nearly 70% of the universe. If dark energy remains constant, the universe may simply continue expanding forever, leading eventually to heat death. But if dark energy's strength increases over time, the expansion does not merely continue, it spirals into runaway growth. Galaxies would accelerate away from one another at such speeds that their gravitational bonds would fail. Stars, once secure in their orbits, would drift apart. Planetary systems would disintegrate. Even atoms themselves, bound by electromagnetic forces, would eventually be torn asunder. The Big Rip unfolds as a sequence of escalating disintegrations. First, clusters of galaxies separate. Then, galaxies themselves are pulled apart. Stars within galaxies lose their grip on orbiting planets. The solar systems dissolve into chaos. In the final stages, stars themselves are torn apart as the very fabric of space expands faster than light can carry the forces that bind matter together. In the ultimate instant, atoms disintegrate, their nuclei split, and even space-time itself rips apart. This ending is not quiet or patient. It is total destruction, leaving not even the possibility of remnants. There would be no black holes evaporating in the darkness, no faint photons drifting endlessly. The Big Rip is absolute, a shattering of the bonds that make existence possible. Though extreme, the Big Rip is not dismissed. It depends on the equation of state of dark energy, the measure of how it evolves with time. Current observations lean toward stability, suggesting dark energy is constant. But the margin for error leaves room for a darker fate. If dark energy shifts, even slightly, the Big Rip could loom in the cosmic future, waiting at the end of time. To imagine it is to imagine the cosmos torn limb from limb. It is not entropy, not collapse, but annihilation through expansion. A universe stretched beyond endurance until it ceases to exist. The terrifying elegance of the Big Rip lies not just in its catastrophic finale, but in the way it redefines expansion itself. In most visions of the universe's fate, expansion is either steady or slowing. Here, it accelerates relentlessly, an unstoppable tide that spares nothing. Galaxies, stars, planets, molecules, each succumbs in turn until no bonds remain to resist the tearing of space-time. The foundation of this scenario lies in dark energy's equation of state, a ratio that describes how its pressure evolves relative to its energy density. If this ratio is exactly -1, dark energy remains constant, like the cosmological constant Einstein once introduced. If greater than -1, expansion slows into a gentler eternity. But if less than -1, what physicists call phantom energy, then the effect is catastrophic. Expansion accelerates not just forever, but ever faster, amplifying its force until it becomes destructive. What is chilling about this model is its predictability. Scientists have outlined a sequence for the Big Rip if phantom energy exists. Billions of years before the final rupture, distant galaxies slip beyond reach. Trillions of years later, galaxies within local groups lose cohesion. Then, just millions of years before the end, solar systems dissolve, planets flung into isolation. In the final days, stars themselves are shredded, and in the last fraction of a second, even atoms disintegrate as space expands faster than the forces that bind particles. The universe ends not with silence, but with shattering. Testing this possibility requires precision. Astronomers use Type Ia supernovae as standard candles, measuring distances across billions of light years. They track the distribution of galaxies with instruments like the Sloan Digital Sky Survey. They measure the cosmic microwave background through satellites like WMAP and Planck. All of these tools seek to constrain dark energy's equation of state, to learn whether it is truly constant or a phantom waiting to unravel existence. So far, the results lean toward constancy, but the margin of error leaves the door open to catastrophe. Philosophically, the Big Rip offers perhaps the most unsettling vision of the end. In the heat death, existence dwindles slowly, a universe slipping into silence. In the Big Crunch, collapse brings a fiery finale, a return to origin. But the Big Rip is annihilation through expansion. It imagines a universe destroyed by its own growth, by the very fabric of space unraveling the bonds of matter. To live in such a universe is to exist on borrowed time, within a structure that is destined not just to fade, but to violently betray itself. And yet, even in its terror, the Big Rip reminds us of something profound, that we are witnesses in an era when galaxies still shine, when planets still orbit stars, when matter still holds together. In a cosmos that may end by tearing itself apart, the present is nothing less than miraculous. Vacuum decay, the quantum betrayal. If the heat death is a slow fading, the Big Crunch a collapse, and the Big Rip a violent unraveling, then vacuum decay is something stranger, an ending that comes not from vast cosmic processes, but from the quantum fabric of reality itself. It is not a fire or a freeze, but a betrayal, the laws of physics suddenly rewriting themselves, annihilating everything we know in an instant. At the heart of this idea lies the quantum vacuum. In everyday language, we call a vacuum empty space. But physics tells us that even the void is not nothing. Space is filled with fluctuating fields, with particles appearing and vanishing, with energy at its baseline state. This baseline is what we call the vacuum state, the ground level of energy for the universe. But what if this vacuum is not truly stable? What if it is only a false vacuum, perched in a valley of energy that is not the lowest possible? If so, then somewhere in the universe, a quantum fluctuation could trigger a transition to a lower energy state. This would create a bubble of true vacuum, a new reality with different laws of physics. That bubble would expand at the speed of light, consuming everything in its path. Galaxies, stars, planets, indeed, the very particles and forces that define them, would be rewritten. Chemistry would vanish, atoms would dissolve, even the constants of nature could change. The universe, as we know it, would end not with violence, but with transformation into something unrecognizable. The terrifying aspect of vacuum decay is its unpredictability. Unlike the heat death, which plays out over trillions of years, or the Big Rip, which would unfold in cosmic stages, vacuum decay would be instantaneous. There would be no warning. One moment, the universe is as it has always been. The next, its rules are rewritten, and nothing survives the transition. Theoretical physics does not dismiss this as fantasy. Calculations involving the Higgs boson, discovered at CERN in 2012, suggest that our universe may indeed be in a metastable vacuum, stable for now, but not absolutely secure. The Higgs field, which gives particles mass, may one day slip to a lower energy state. If so, the seeds of vacuum decay are already present, waiting in the quantum fabric. Yet if this is the end, it is also strangely merciful. For those within the universe, vacuum decay would be painless. There would be no anticipation, no suffering, no lingering shadow of collapse. The end would be instant, silent, and absolute. Philosophically, vacuum decay is both terrifying and humbling. It suggests that the universe is not guaranteed, that even the laws we take as eternal may be temporary scaffolds. It reminds us that existence itself is fragile, balanced on a knife edge of quantum fields, and it forces us to confront the possibility that reality could, without warning, give way to something else entirely. To imagine vacuum decay is to confront the fragility of reality itself. Unlike other cosmic endings, which depend on the visible dance of stars and galaxies, this scenario emerges from the invisible structure of quantum fields, the fabric that underlies all existence. In this sense, vacuum decay is not merely an astronomical theory, but a revelation of how tenuous the rules of our universe might be. The concept gained urgency with the discovery of the Higgs boson in 2012. The Higgs field gives particles their mass, and its measured properties suggest a precarious balance. The universe may exist in a metastable state. Imagine a ball resting in a shallow valley. From our perspective, it seems stable. It sits still, unmoving. But beyond the ridge lies a deeper valley. If the ball were to cross, it would roll down into a new state of stability, an entirely different configuration. In the same way, our universe may sit in a false vacuum, safe for now, but vulnerable to a sudden shift. What would trigger such a transition? Perhaps a quantum fluctuation in some distant region of space. Perhaps a violent collision of high-energy particles, though current physics suggests even our most powerful accelerators cannot produce such an event. Once initiated, however, the bubble of true vacuum would expand at the speed of light, rewriting the rules of physics as it grew. No warning could outrun it. No escape would be possible. Scientists study this possibility by calculating the stability of the Higgs field and its interactions with other fundamental forces. If the Higgs boson is heavier or lighter than expected, the balance shifts. Current data suggest metastability. The universe is not perfectly safe, but neither is decay imminent. The timescales involved may exceed the age of the universe by orders of magnitude. Yet the possibility remains, lodged in the equations, a faint shadow at the edge of existence. Philosophically, vacuum decay is a paradox. It is both terrifying and oddly merciful. Terrifying because it implies that the laws of nature themselves may not be eternal, that what we call physics is not absolute, but conditional, temporary, fragile. Merciful, because if it comes, it will be instant, painless, and complete. There will be no cosmic suffering, no slow fading into oblivion. One reality ends, another begins. But what becomes of that new reality? Would the true vacuum host stars, galaxies, and life? Or would it be barren, a realm of physics hostile to complexity? We cannot know. The bubble would be alien, its laws incomprehensible, its structures unknowable. To us, it would be annihilation. To physics, it would simply be change. In this sense, vacuum decay forces us to confront an uncomfortable truth. The universe is not obligated to preserve us. Its laws are not written for our comfort. They are provisional, the outcome of fields and energies that may themselves be subject to deeper rules. If vacuum decay is possible, then existence itself is contingent, its stability a temporary accident in an endless quantum sea. And yet, rather than despair, some find awe in this idea. For it means that our universe is special, a bubble of stability that allowed galaxies to form, stars to shine, life to arise. If it is temporary, then our existence is all the more precious. We live in a fragile cosmos, balanced on quantum edges, yet filled with beauty, light, and meaning. Vacuum decay may never come. The universe may endure for trillions of years, its metastability effectively eternal. But the possibility lingers, whispered in the equations of particle physics, reminding us that permanence is an illusion. The ground beneath our existence is not absolute. It is a delicate, shimmering field, capable of betraying us at any moment. The black hole era, long after the last stars have burned out, after galaxies have grown cold and silent, a new age will begin. A cosmic chapter ruled by the most mysterious and powerful objects in existence, black holes. These remnants of collapsed stars and galactic cores will dominate the universe, standing as the final titans of gravity in a cosmos otherwise fading into emptiness. Astronomers call this distant future the black hole era. To understand how we arrive here, imagine the universe after trillions of years. By then, stars have exhausted their fuel, and stellar birth has ceased. White dwarfs have cooled into invisible black dwarfs. Neutron stars have grown cold and inert, and the only sources of gravitational drama that remain are black holes. They are the last engines of energy, the final arenas where matter and space-time wrestle with each other. Black holes are born from collapse. When massive stars die, their cores collapse under gravity's weight, crushing matter into Xian, densities so extreme that not even light can escape. Supermassive black holes, meanwhile, form at the centers of galaxies, swallowing stars and gas, binding billions of suns into their gravitational grip. In the black hole era, these objects will be the ultimate survivors. Yet even black holes are not eternal. Stephen Hawking showed that they emit faint radiation, now called Hawking radiation, a quantum effect in which particle-antiparticle pairs near the event horizon allow energy to leak away. Over unimaginable timescales, black holes slowly evaporate, shrinking until they vanish in a final burst of energy. In the black hole era, the universe becomes a stage for this evaporation. Small black holes vanish first, while larger ones linger. Supermassive black holes, millions or billions of times the mass of the Sun, will endure the longest, their lives stretching across 10 to the 100th power years or more. During this time, they will consume any matter drifting near, merging occasionally when galactic cores collide. But eventually, even they will fade, their titanic gravity dissolving into a faint whisper of radiation. The universe in this age is almost unrecognizable. There are no shining stars, no glowing nebulae, no galaxies blazing with light. Instead, darkness rules. Black holes drift silently, their event horizons marking the last places where matter still clings to existence. Around them, space is vast and cold, with only occasional bursts of activity as they merge or consume the remnants of fallen stars. For any observer, if any could exist, it would be a universe of shadows, punctuated only by the strange phenomena of black holes. The death spiral of matter falling inward, the gravitational waves ringing through space when two black holes merge, the quiet evaporation as Hawking radiation steals away their mass, these would be the last sources of cosmic drama. The black hole era is both terrifying and majestic. It is the age of gravity's ultimate triumph, the moment when the most extreme objects outlast all others. Yet, it is also an age of decline, for even black holes cannot escape time. Their slow fading marks the final act of structure in the cosmos. The last resistance before entropy claims everything. The black hole era is perhaps the most haunting chapter in the cosmic story. For in this epoch, even the last survivors of stellar death, the black holes themselves, begin to surrender to time. Gravity may seem invincible, a force that bends space-time, traps light, and swallows entire stars. Yet quantum physics whispers another truth. Even black holes are not eternal. Stephen Hawking's insight in the 1970s revealed that black holes emit radiation. Near the event horizon, quantum fluctuations create pairs of particles and antiparticles. Normally, these annihilate instantly, but if one falls into the black hole while the other escapes, the escaping particle becomes real radiation. To conserve energy, the black hole loses a tiny fraction of its mass. Over vast spans of time, this process, now known as Hawking radiation, causes black holes to slowly evaporate. The evaporation is unimaginably slow. A black hole with the mass of a star could take 10 to the 67th power years to vanish. Supermassive black holes, billions of times heavier than the Sun, would persist even longer, enduring for 10 to the power of 100 years or more. During this era, the universe will be dark, yet not completely silent. As black holes shrink, they grow hotter, their radiation more intense. In their final moments, they would emit bursts of energy, the last flickers of light in a cosmos already emptied of stars. Between these deaths, the universe drifts toward stillness. Black holes may collide, merging into larger monsters, their cataclysmic crashes sending ripples of gravitational waves across space-time. Yet even these events grow rarer as galaxies thin out, stars vanish, and matter becomes scarce. Eventually, each black hole stands alone, evaporating in isolation, leaving behind nothing but faint radiation stretched thin by expansion. Philosophically, the black hole era is unsettling because it represents not just the end of stars or galaxies, but the end of structure itself. Black holes are the last repositories of order, holding mass, energy, and information within their horizons. Their evaporation marks the final dissolution of this order, the last surrender to entropy. When the last black hole dies, the universe will cross into the dark era, an existence stripped of all structure, where only thin radiation remains. And yet, there is a strange beauty in this vision. Black holes, once feared as destroyers, become the last sources of energy in the cosmos. Their slow evaporation gives the universe its final flickers of light. They are both grave and lantern, devouring the past yet illuminating the end. In their death throes, they ensure that nothing resists entropy forever. When the black hole era passes, time will not stop. But the story will grow quiet. The cosmos, emptied of stars, galaxies, and black holes, will enter a silence deeper than anything we can imagine. A silence not of peace, but of inevitability, proton decay, and the end of matter. If the black hole era represents the slow evaporation of the universe's last giants, then proton decay introduces an even more unsettling possibility: that matter itself may not endure. Stars, galaxies, and black holes are dramatic, but they are all built from the same foundation: atoms. And atoms, in turn, are built from protons, neutrons, and electrons. If the proton, the stable heart of atomic matter, is not eternal, then the very building blocks of reality are doomed to vanish. In our daily lives, protons appear timeless. They are the positively charged cores of hydrogen atoms, the most abundant element in the universe. Alongside neutrons, they form the nuclei of every atom heavier than hydrogen. For all of recorded history, and indeed for billions of years, protons have appeared unchanging. Unlike neutrons, which decay in about 15 minutes outside the nucleus, protons seem perfectly stable within it. Without their persistence, matter as we know it could not exist. Yet grand unification theories, the ambitious frameworks that seek to merge the strong, weak, and electromagnetic forces, predict that protons may not be perfectly stable. They may decay, albeit over timescales so vast they make the black hole era look brief by comparison. According to these theories, protons could spontaneously transform into lighter particles, such as positrons and neutrinos, releasing a faint flash of energy in the process. Experiments have searched for this decay. Massive underground detectors, such as Super Kamiokande in Japan, have monitored vast volumes of water, hoping to catch the telltale signal of a proton's death. So far, none have been observed. These experiments have set lower limits on the proton's lifetime. It must endure for at least 10 to the 34th power years, and perhaps far longer. But the possibility remains open that, given enough time, protons do decay. If this is true, the implications are profound. It means that even after the last black holes evaporate, the universe's story is not finished. Slowly, atom by atom, matter itself will dissolve. Hydrogen atoms, the simplest and most numerous, will vanish first. Heavier atoms will follow, their nuclei disassembling into light particles and radiation. Over unimaginable spans of time, entire galaxies of cold, dead matter will fade into a haze of subatomic ghosts. In such a future, the universe becomes ever more empty. Not only stars and planets are gone, but the atoms that once composed them. No solid matter survives. No chemistry is possible. The cosmos reduces to a thin mist of electrons, neutrinos, photons, and whatever particles endure beyond the death of protons. The vision is chilling because it strikes at the foundation of existence. Matter is the scaffolding of reality, the substance of stars and life alike. If protons decay, then even this scaffolding is temporary. The universe is not built on permanence, but on processes that erode, slowly but inexorably, toward nothingness. And yet, as always in cosmology, there is awe in the vastness of the timeline. Proton decay, if it occurs, will take longer than any human imagination can truly grasp. Entire civilizations could rise and fall 1 trillion times before a single proton decays. Stars could live and die, galaxies could form and collide, and still matter would remain. But the mathematics of physics suggests that permanence is an illusion, even here. The search for proton decay is one of the most ambitious quests in modern physics. To detect it, scientists must look for impossibly rare events. One proton among an ocean of particles spontaneously breaking apart. Since protons are unimaginably long-lived, experiments require vast detectors and decades of patience. Deep underground, in places shielded from cosmic rays and background noise, Physicists construct enormous chambers filled with ultra-pure water or liquid scintillators. Detectors like Super Kamiokande in Japan or the proposed Hyper Kamiokande are designed to catch the faintest flashes of light produced when a proton decays. Billions of tons of protons are monitored, waiting for one to fail. To date, no confirmed proton decay has been observed, but every null result pushes the lower limit of the proton's lifetime further, suggesting lifespans exceeding 10 to the 34th power years. This number is staggering. It dwarfs the age of the universe, which is only about 10 to the 10th power years. Yet even these lifetimes are not infinite. Physics whispers that permanence may still be an illusion. If protons do decay, the universe's long future grows even bleaker. After the black hole era, when the last remnants of stars evaporate, a new epoch would begin, the decay era. During this time, matter itself unravels. Hydrogen, helium, and heavier nuclei gradually fall apart. Galaxies that once blazed with light and later became graveyards of stellar corpses dissolve into a haze of elementary particles. Structures vanish, chemistry becomes impossible, and solidity disappears. The cosmos in this era would be eerily featureless. No stars, no planets, no black holes, just a thin, fading mist of leptons, photons, and neutrinos. Even atoms, which have endured since the first minutes after the Big Bang, would no longer exist. The familiar world of matter, the world of stone and bone, of oceans and air, would be erased. Philosophically, this possibility is deeply unsettling. For billions of years, life and civilizations have taken matter's stability for granted. We build our bodies, homes, and technologies on the assumption that atoms endure. But proton decay suggests that even this foundation is temporary. Everything we touch, everything we know, is destined to dissolve. Permanence is a fleeting illusion, even at the most fundamental level. And yet, there is another way to see it. If protons eventually decay, then matter itself becomes part of the universe's grand cycle of transformation. Just as stars die and scatter their elements, so too would matter give way to new forms. Existence is not destroyed, but altered, rewritten in particles and radiation that continue the cosmic story. For now, we live in a universe still rich with matter. Protons endure long enough to build galaxies, stars, and life. The decay era lies so far in the future that it is almost beyond imagination. But in the mathematics of physics, it is there, a reminder that nothing, not even atoms, lasts forever. The dark era. After the black hole, era fades, and after the last protons decay, the universe enters its final act, the dark era. This is the end of structure. The silence after all celestial drama has concluded. No stars burn, no galaxies glow, no black holes dominate the centers of space. The cosmos becomes an endless expanse of emptiness, filled only with the faintest whisper of radiation and particles drifting apart into infinity. The transition into this epoch is gradual, stretched across timescales that dwarf comprehension. By the time the last black hole evaporates in a final burst of Hawking radiation, the universe is already unimaginably old. The vibrant structures of the early cosmos, nebulae, galaxies, stars, are long gone. Even the faint remnants of matter are dissolving into radiation. What remains is a universe stripped bare, where entropy has triumphed completely. In this era, the cosmos is not dead in the sense of ceasing to exist. Rather, it is exhausted. All usable energy has been spent. Temperature differences no longer exist. Gradients that once powered stars, life, and structure have flattened into equilibrium. The universe cools asymptotically toward absolute zero. There are no more engines of creation, no sparks of novelty. The fabric of space-time itself continues to expand, carrying the last particles farther and farther apart. Electrons, neutrinos, and photons drift endlessly, so dilute that the chance of collision approaches zero. If protons decay, then atoms no longer exist. If they do not, they will remain locked in an infinite, frozen dispersal. Either way, complexity is gone. Philosophically, the Dark Era is perhaps the most haunting of all. It is an ending without spectacle, a conclusion not with fire or collapse, but with silence. No witness could exist to see it. No memory could persist. The universe, once filled with brilliance and structure, ends as a shadow, a quiet void where time itself seems meaningless. And yet, within this vision lies a kind of austere beauty. The Dark Era is the purest expression of entropy, the ultimate balance. It is the cosmos at rest after eons of turbulence. It is stillness, absolute and eternal. The Dark Era is often described as the ultimate silence, the point where the universe ceases to change in any meaningful way. Yet within this silence, theoretical physics whispers possibilities, strange, speculative visions that suggest the end may not be final after all. Even in a cosmos stripped of stars, galaxies, and matter, quantum mechanics insists that emptiness is never truly empty. The vacuum is restless. Tiny fluctuations ripple through space-time, birthing virtual particles that appear and vanish in instants too brief to measure. In the Dark Era, when everything else has faded, these fluctuations remain. Some cosmologists speculate that, given enough time, they might seed new beginnings. One possibility is that a quantum fluctuation could ignite a new Big Bang, inflating into another universe with its own space-time, forces, and particles. Our cosmos may then be only one in a vast multiverse, each born from the silence of others. In this way, the Dark Era is not an end, but a womb, the stillness before another birth. Another speculation involves Boltzmann brains, self-aware entities that, in the infinite, timescales of the Dark Era, might spontaneously form from random fluctuations in the void. Though improbable, infinity allows for even the most bizarre possibilities. Such minds would live briefly, surrounded by nothing, before dissolving back into chaos. It is a vision both absurd and haunting, raising questions about whether our own existence might be one such fluctuation. And then there is the question of time itself. In the Dark Era, when no processes occur, does time still have meaning? Without stars to measure, without change to mark, does time flow, or does it stand still, frozen in the stillness of entropy? The universe may continue expanding, but in practical terms, it will have reached a state where nothing happens. Philosophically, the Dark Era confronts us with the starkest possible truth. Endings are real. Not dramatic endings of fire or collapse, but endings of silence. And yet, even here, physics offers hints that stillness might not be final. The cosmos could be cyclical, reborn endlessly in new forms. Or it could dissolve permanently, leaving behind only the memory that once, long ago, galaxies burned bright and life emerged from starlight. If there is meaning in such an end, it is this: that impermanence does not diminish existence, but makes it more extraordinary. The brilliance of galaxies, the spark of life, the wonder of consciousness, all arise in a universe that will one day fall silent. We live in the brief interval where the cosmos is awake, and it is in this fleeting light that meaning is found. Speculative escapes. The universe may be destined for silence, collapse, or rupture. Yet throughout history, humans have resisted inevitability. Faced with cosmic endings, scientists and philosophers have asked, is there a way out? Could intelligence, physics, or sheer ingenuity allow life to endure beyond the universe's death? These are not answers, but questions woven into speculative science, bold attempts to imagine survival when everything else fades. One possibility lies in wormholes, hypothetical tunnels through space-time predicted by general relativity. If such structures exist and could be stabilized, they might connect our universe to another, providing an escape hatch before the final collapse or fade. Wormholes, however, remain uncertain. They appear unstable, requiring exotic forms of matter to prevent collapse. Yet the mathematics does not forbid them entirely, and for some, this offers a fragile thread of hope. Another speculation is the multiverse. If our cosmos is only one bubble among countless others, perhaps intelligence could migrate between them, or at least pass information forward. In eternal inflation theories, universes continuously spawn, each with different physical laws. Ours may die, but others may thrive. The question is whether life, or its descendants, could ever bridge these gulfs. Technology itself could become a form of escape. Some have imagined civilizations far in the future, building vast computational structures designed to simulate entire realities. These digital refugees could persist until the very last usable energy is consumed. In this vision, life does not escape death, but prolongs meaning within it, extracting every possible moment of thought from the fading cosmos. And then there are the strangest proposals: harvesting energy from black holes, storing it against the dark, creating artificial universes in laboratory conditions, birthing new realms in which life might continue, or even attempting to alter the constants of physics themselves, reshaping reality to stave off entropy. Each is fantastical, yet each arises from serious consideration of physics pushed to its limits. The speculative escapes remind us of two truths. First, that endings are written into physics, and second, that the will to endure drives imagination beyond those boundaries. The universe may close every door, but intelligence seeks windows. The dream of escaping cosmic death stretches the imagination of science and philosophy alike. If the universe is doomed to silence or collapse, then perhaps survival lies not in resisting, but in transforming, finding ways to prolong meaning, memory, and thought, even as physics closes its doors. One vision is the construction of Dyson spheres or swarms, colossal megastructures encircling stars to capture nearly all their energy. In a dying universe, such technology could extend life for trillions of years, feeding civilizations on the faint embers of red dwarfs. Yet even these stars will fade, and Dyson spheres cannot resist entropy forever. Still, they represent a testament to the will to endure, extracting every possible drop of light from the cosmos. Another idea lies in vacuum fluctuation universes. If quantum fluctuations can give birth to universes, might an advanced civilization someday learn to harness them? Perhaps they could ignite a bubble of new spacetime, creating a universe in which life continues. If such a feat were possible, our universe might itself be the creation of beings from a previous cosmos, passing forward the possibility of survival. Some scientists and philosophers suggest that consciousness itself might escape physics if uploaded into digital substrates. Vast computational networks could store minds, living within simulations until the last energy flickers out. This digital eternity would not outlast entropy, but it could extend meaning deep into the universe's twilight. To some, this is survival. To others, it is a tragedy, life reduced to thought in a box, awaiting inevitable silence. And yet, these visions face a deeper question. Is survival the goal, or is acceptance? Physics may allow no escape from entropy, collapse, or decay. In that case, meaning lies not in escaping endings, but in embracing impermanence. The fact that we live in a universe where stars shine, galaxies blaze, and life exists, briefly against the backdrop of eternity, may itself be enough. Speculative escapes remind us of two truths: that intelligence dreams beyond its limits, and that every dream is shaped by the laws of physics. Whether or not escape is possible, the act of imagining it reveals something profound. The cosmos may be indifferent, but life resists silence with thought, creativity, and wonder. Philosophical reflections. The fate of the universe is written in equations, but its meaning cannot be captured by numbers alone. Heat death, big crunch, big rip, vacuum decay. These are physical possibilities, scientific hypotheses. Yet beneath them lies a deeper question. What do such endings tell us about ourselves, about life, and about the search for meaning in a cosmos destined to end? At first glance, the universe's mortality seems bleak. To know that galaxies will vanish, stars will fade, and even matter itself may dissolve is to confront the fragility of everything we cherish. Civilizations rise and fall in the blink of cosmic time. Human history, with all its triumphs and tragedies, is but a flicker against the backdrop of eternity. In a universe that will one day grow silent, does anything we do matter? And yet, to frame the cosmos in this way is to miss its gift. The universe does not owe us permanence. Its brilliance lies precisely in its impermanence. Stars shine because they burn. Galaxies blaze because they evolve. Life exists because energy flows. The very processes that guarantee endings are the same processes that made beginnings possible. Without entropy, there would be no arrow of time. Without change, there would be no life. The universe's mortality is not a curse, but a condition of its beauty. For humanity, this realization is both humbling and liberating. It reminds us that meaning is not found in eternity, but in presence. We exist in a rare and extraordinary moment, a cosmos alive with stars, rich with complexity, fertile with life. We live in an age when the night sky is full of galaxies, when the universe is young enough to blaze, but old enough to host observers. To be conscious in such a time is a miracle of chance, a fleeting but profound privilege. The endings of the universe, then, are not only scientific forecasts, they are philosophical mirrors. They ask us to consider what we value in the face of impermanence. If all things fade, then meaning must be made now, in the finite light of our epoch. Some may find comfort in speculative escapes, multiverses, wormholes, rebirths. Others may find comfort in acceptance, in the idea that transience itself is enough. Either way, the lesson is clear. Existence is temporary, but not empty. Its brevity sharpens its beauty, and its fragility deepens its worth. In this sense, the story of the universe's end is also the story of human perspective. For though we cannot halt entropy, we can embrace the miracle of being here, now, in a cosmos still filled with light. If science provides the mechanics of the universe's end, philosophy provides its meaning. Across cultures and traditions, humanity has always looked to the heavens to understand mortality, not just our own, but the mortality of everything. When we learn that the cosmos itself will one day fade, collapse, or unravel, we are invited to ask not only what will happen, but what it means. Different cultures might interpret this impermanence in profoundly different ways. In Buddhism, impermanence is not tragedy, but truth. The universe's transience is a mirror of life itself, where change is the only constant. The cosmic fade of heat death could be seen not as failure, but as release, the final dissolution of all attachments. By contrast, Western traditions, steeped in the search for permanence, might find the same fate unsettling, a reminder that nothing is immune to time's erosion. Philosophers from the Stoics to existentialists remind us that endings, far from negating meaning, sharpen it. Marcus Aurelius wrote that the brevity of life is what makes it valuable. Camus argued that meaning arises from embracing life in spite of its inevitable end. In the same way, knowing the universe itself is mortal transforms the present into something extraordinary. We live not in an eternal cosmos, but in a fleeting golden age where stars still burn and life still thrives. This cosmic perspective breeds humility. Civilizations often imagine themselves central to history, yet our entire species is a brief moment in a vast story. The Milky Way existed for billions of years before us, and it will continue long after we are gone. To grasp the universe's mortality is to recognize our place within it, not as masters, but as participants in a fleeting chapter. But there is also hope. If the universe teaches anything, it is that endings and beginnings are intertwined. Stars die to create the elements of life. Galaxies collide to seed new forms. Even the darkest fates may give rise to unknown possibilities, new universes, new structures, perhaps even new kinds of existence beyond our imagining. The universe may end, but its story is not only about death, it is about transformation. To reflect on its endings is not to despair, but to marvel that, for a brief time, we exist in the light between the darknesses. The story of the universe is a story of light and darkness, of birth and death, of beginnings woven seamlessly into endings. From the first instant of the Big Bang to the possibilities of heat death, crunch, rip, or decay, the cosmos has carried us on a journey vast beyond comprehension. And yet, every ending we have explored is not just a conclusion, but a transformation. In the heat death, stars fade, galaxies vanish, and time drifts into silence. In the Big Crunch, gravity's relentless embrace pulls all things back into a final inferno. In the Big Rip, expansion accelerates until even atoms are torn apart. In vacuum decay, reality itself betrays us, rewriting the laws of existence. And in the slow decline of proton decay and the dark era, the scaffolding of matter dissolves, leaving only emptiness behind. Each ending is distinct, yet each is bound by the same truth. Nothing is permanent. Permanence is the illusion of the present, a trick of our brief perspective against the backdrop of eternity. But this impermanence is not despair, it is meaning. The fact that stars will die makes their light more precious. The fact that galaxies will fade makes their brilliance more extraordinary. The fact that life exists in such a fleeting window of cosmic time makes it miraculous. We live in a universe that is temporary, and that is precisely why it matters. In the end, the universe will not remember us. The atoms of our bodies will dissolve, the light of our civilizations will fade, and the story of humanity will be written only in echoes that no one will read. But we remember the universe. We look to the stars, trace their fates, and in their stories we find our own. For all its endings, the cosmos has given us this, the gift of existence in a moment when stars still shine, when galaxies still blaze, when life is possible. We are the universe looking at itself, aware of its own impermanence, able to find wonder even in the certainty of silence. The universe may end in fire, in ice, in rupture, or in silence. But while it lasts, it burns with light, and within that light we find meaning.